Welcome everybody. Let's click this. My name is Dave Addison. I'm the IAPWS Power Cycle Chemistry Chair at the moment, and I'd like to welcome you all to the first ever IAPWS PCC webinar that we'll be doing. So I'm just going to say a few words quickly and introduce IAPWS for anyone who's not super familiar with it. IAPWS, it's the International Association for the Properties of Water and Steam, and we're here to advance knowledge of the properties of water, steam, aqueous systems, particularly those properties and guidance of industrial importance, and to make that knowledge freely available to engineers and scientists the world over. So these webinars are part of that mandate to do things, do a few new things, but we have lots of information on the IAPWS website and lots of guidelines and things like that that'll come to quickly. And Barry will be talking about those as well later on. IAPWS has been around since 1929. It's an association of national organisations. I wear a couple of hats in IAPWS. I'm also the chair of the New Zealand branch as well, and it's managed by an executive committee, meets annually. Next meeting is coming up in Helsinki in June, and everyone's invited, and we try and hold a conference every 4 or 5 years, and every year we have a working meeting that everyone's welcome to come to. Members at the moment, our official members are Australia, Canada, Germany and Switzerland, New Zealand, the USA, our Nordic friends, combination Denmark, Finland, Norway, Sweden, IAPWS, which is Britain and Ireland, Czech Republic, Japan, and Russia is currently suspended. And then we have a second tier, which is associate members, which are countries that are forming their national committees and coming into IAPWS. So there's a few of those there you can see. IAPWS is made up of multiple working groups. We have an executive committee. We have the thermophysical properties of water and steam, TPWS. So that's where steam tables come from. So anyone from a power station background will know about those. We have industrial requirements and solutions, which is a lot of the steam turbine manufacturers are involved in that. The physical chemistry of aqueous solutions group, PCAS, and this is the universities and the research people. And down the bottom is little old power cycle chemistry, we're the practical cousins of IAPWS. We are the power plant, the water, steam, the industrial people. So we work in that area. Steam tables from all around the world. IAPWS IF95 is the primary document, and this is the basis of every steam turbine, every steam power plant in the world is designed around IAPWS steam tables. And there's a whole bunch of examples from Barry here from around the world that have been taken from the IAPWS and turned into sort of national documents. But without IAPWS steam tables, you wouldn't have any fossil or industrial or geothermal or nuclear power stations, because you wouldn't be able to design them properly. In terms of PCC, here's our current chairs or vice chairs. So it's myself from New Zealand, there's Paul McCann from the UK, Kirk Butcher from the USA, and Tara Ichihara from Japan. And you can go on the IAPWS website and you can find our details to contact us if you have any questions. Barry will be talking about these, but if you go to the IAPWS website and then click through onto tech guides, you'll find all of the technical guidance documents. So these are all of the guidelines for power plants, industrial plants, everything to do with water and steam, and these are all free to download. You can download them as PDFs and use them to your heart's content. Upcoming meetings, as I mentioned earlier, we've got our annual meeting coming up 22nd to the 27th of June in Helsinki, and if you click on the IAPWS website you can find information about that meeting. There's a couple of related events, the HRSG forums, there's one coming up in the US and one coming up in Latin America, and there's always a lot of IAPWS related information on there, and Barry and Bob and Scott are heavily involved in those. And then we have a similar one down in Australia at the end of the year, ABHUG, Australasian Boiler HRSG User Group. And that's a pretty good event as well if you're down that way. And lots of the national committees have meetings and events as well. So without any further ado, I'm going to hand you over to Barry Dooley, who has been a very long time part of IAPWS and part of the PCC. And he's going to take us on a webinar today, and there'll be an opportunity to fire your questions through in the chat, and then we'll have a go at Barry will have a go at answering those at the end. So Barry, I'll hand over to you, mate. It's all yours.
Okay. Here, just got to share this. There we go. Is that okay? Scott, is that okay?
Yes, Barry, looks great.
Thank you. And I just got to find my laser pointer. Here. So good morning, good afternoon, wherever you are. I don't see a list of all the people that are here, so I don't know where you're from, but I saw some of the registrations, so it looked like we had people from all over the world. What I'm going to try and do in the next 45 minutes is try to cover how the IAPWS technical guidance documents, which David just showed you off the website, address the major power plant cycle chemistry influence related damage and failures, and how they're influenced by what we call repeat cycle chemistry situations. And I'll introduce all those to you. I'm going to try and give you a little bit of background as we go through here on some of the technical guidance documents on each of them, to cover some of the items which I find when I tour the world and visit many of your plants are missing understanding. So I'm going to try and cover those as well. So I think we're okay here, and so I'm going to start here today where I usually finish, and I'm going to do that so that I can just introduce a little bit more in detail of what David has already showed you. There's currently 11 technical guidance documents, and they're covered here in this part. These this information in yellow here are the numbers that you can take them off the website. And what I put here is a diminutive by which we know these technical guidance documents. And you're going to see these a few times during the presentation today. So I'm just going to very quickly just indicate to you that this first one is on carryover of impurities into steam. This one is on the instrumentation that's required in each and every power plant or fossil and combined cycle plant. This one is one of the major treatment guidance documents. So this is on volatile treatment, so that means for AVT and OT. And next one. Well, I've just got to go here. How do I get this thing to change? And this next one here is the other treatment document on phosphate and sodium hydroxide. We call this PT and CT. This is the major document on steam purity. Tells you everything about the guidance for steam, and introduces you to some of the failure mechanisms, which I'll talk towards the end of this presentation. Corrosion products is very important, as you'll see, probably the most important. This tells you how to measure them, sample them, and analyze them properly. This one here is the other important document for HRSGs in HP evaporators to identify the deposits, how to sample for the deposits, and what that result then means in terms of how we can move ahead with the HRSG. There are two guidance documents on film forming substances. This is the first one. This is for fossil and combined cycle plants. The other one is for industrial plants. This document at the bottom is for air and leakage. And this is the industrial plants film forming substances. And then the final one is on the management of generator water cooling. So they're the major documents that I wanted to introduce here at the beginning, and you'll see as we go through in indications like this and like this, indicating how the IAPS documents cover the major failure and damage mechanisms that are influenced by the chemistry. So having done that for introduction, let's just now move ahead in terms of why and how these technical guidance documents have been introduced. There are basically two factors that have driven the introduction and development of these technical guidance documents for fossil combined cycle plants. The first item is to delineate the major damage and failure mechanisms that are influenced by the cycle chemistry. So what are they? And the second item that we need to take into account is on the statistics on deficient and non-optimum cycle chemistry processes. We call these repeat cycle chemistry situations, RCCS, and you're going to hear quite a lot about those as we go through this in the next half an hour. So hold on. So first of all, let's have a look at the what we consider to be the major cycle chemistry damage mechanisms in these plants. First of all, of course, are tube failures. Tube failures are probably the most important, and there's two that we're really interested in. One is flow accelerated corrosion, and this, of course, is the leading tube failure mechanism in HRSGs, and it's a major safety issue in fossil plants. And under deposit corrosion, there's really only one now. There used to be three, but there's only one now that we're really worried about, hydrogen damage, and that still occurs. For instance, there was two major hydrogen damage failures in the last 2 weeks in a country. And so then we have to look at the corrosion products that are transported from the lower pressure circuits due to inadequate feed water chemistry. And this is important because these corrosion products actually give rise to the deposition that results and causes these tube failure mechanisms. There's an importance of having an ACC in the cycle. If the chemistry isn't correct for these plants, the plants will typically have up to 100 ppb of iron. And then the third area is the steam turbine, where we have deposits, damage and failure, not at the same frequency, of course, as the tube failures, but most important, there are probably between 5 and 7 each year that I either deal with or am asked to provide some guidance on. And these are things like pitting on the blade surfaces, stress corrosion cracking, and corrosion fatigue, which are basically the leading chemistry influenced steam turbine failure mechanisms. And these are resulting from the lack of shutdown protection, which we'll talk about towards the end of the presentation. So what are the main indicators of damage and failure? I've already indicated that we call these repeat cycle chemistry situations, and from the data that we have, you'll see this in a couple of slides, confirms that these failure and damage that we've just talked about are not random, but are controlled by plants operating with multiples, 2 or more of RCCS, and they relate to these 9 items. I'm not going to go through these now because we're going to cover these in some detail, but basically you can look upon them as deficiencies in cycle chemistry control of plants. And so to give you an indication of what they are, I've included a couple of examples here, not for all of them, just for 3 of these. And so for corrosion products, we most often find these 2 at the top. The corrosion products are not known in plants, and very often they're too high and above local guidance values. These are the two main ones for corrosion products, but there are others here that you can read. HRSG, HP evaporator deposits. So these are very important because these are the items that control those failure mechanisms under deposit corrosion. HP evaporator samples are not being taken. So that means that there's no knowledge of deposit levels or the deposition rate. And sometimes the deposits are very high, as I'll show you a little later, and very often not linked with the chemistry or the FAC in other parts of the cycle. And the third one I just want to introduce is on what we call challenging the status quo, with the probably most frequent is plants continuing to operate with the chemistry that's been there since commissioning. So therefore, using incorrect or outdated guidelines, continuing to use a couple of the chemistry treatments, phosphate treatment, most often still using congruent phosphate treatment instead of phosphate treatment with only trisodium phosphate. Continuing to use reducing agents in combined cycle plants. This is a very common one, which results in FAC, and is very frequent in all ferrous fossil plants as well. So you can see that this would lead to this one here, where there's some misunderstanding between two of the major chemistries, the oxidizing chemistry AVTO and the reducing chemistry AVTR. And so hopefully this gives you some idea of what these RCCS are. And the next thing I wanted to cover was looking at the international statistics for these. I just updated this table that I'm going to show you next in March for the Australian IAPWS symposium that was in Queensland that I went to, and so this is the table here, and you can see that these are the categories that we just introduced, the repeat cycle chemistry situation categories. This is the data for fossil plants, and this is the data for combined cycle HRSG plants. And the numbers on the table here represent the percentage of those total plants that have these items as RCCS. And so you can see that this provides a ranking. So the most important one being all the aspects involved in corrosion products, not measuring them, operating with them too high. Online instrumentation, not having the required instrumentation. Drum carryover, measuring the carryover of impurities into steam. And the fourth one, not challenging the status quo in some of the areas that I talked about, usually using the wrong chemistry or using the wrong chemistry for too long. So this table very nicely provides an overall ranking of the major chemistry activities and where IAPWS guidance is most needed. So this is a very powerful table for us in IAPWS. It tells us that these are the things that we need to address and have as guidance documents in the world. So let me see if I can get the next slide here. So let's now look at the other aspect. I want to illustrate the importance of RCCS as compared to operating with the optimum chemistry. What's the difference between a plant operating with all the features that are already included in the guidance documents and a plant that has multiples RCCS? We need to look at some of the examples of cycle chemistry influence, damage, and failure, and how the IAPWS TGD, which I introduced, address all aspects and should be incorporated into the design by the manufacturers originally we're trying to work on that aspect. We have been for some time, and operation with the plants, and that's up to people like yourself using these guidance documents. So to illustrate this, what I've done is just selected four damage and failure mechanisms here, right here, and I'm going to go through each one, tell you which parts of RCCS contribute to these and which of the IAPS documents directly address these problems. So the first one, we'll look at under deposit corrosion and hydrogen damage. And so here are a couple of examples: under deposit corrosion, hydrogen damage in HRSG, HP evaporators. And you can see here the inside surface looks a little dirty, very heavy deposits. If you cross-section it, you can see those heavy deposits and the corrosion that takes place right here. And down here is where we've conducted a metallurgical examination. You can see the very heavy corrosion products. And when we look at these in detail, you can see it most often looks like this in a laminated structure. This laminated structure indicates that the rate is very fast. It's a linear corrosion rate, and that's why these are so important. Eventually, we get a brittle failure, as you can see right here. And if we look at the same mechanism in fossil plants, you can see again the examples of the brittle failure that takes place, initiated by heavy deposits on the internal surface. Here's the heavy deposit on those internal surfaces. And when we look in detail with analytical microscopy, we find that along this interface here, we usually have a chloride, and this chloride is there because it's concentrated at the bottom of a heavy deposit. It won't concentrate at the bottom if the deposit is only thin. So this is a key part of the hydrogen damage under deposit mechanism. So this is the first slide that I'm going to show you like this. I'm going to show you 4 of them. So I'll just introduce this. With a little longer. So these are the RCCS which we've observed. All have been observed in hundreds of case studies, but there are IAPS technical guidance documents to avoid. So we'll look at these. I'll name them all in a minute. And this in yellow over here are taken those diminutives from the first couple of slides that I showed you. So these are the technical guidance documents that address these RCCS. So in the first cases are due to those corrosion products, with the corrosion products exceeding international guidance values, sometimes not monitored, and measuring the wrong part of the corrosion products, measuring only the soluble part. And so from IAPS point of view, these IAPS documents on corrosion products and the new one on the new white paper will address each one of these RCCS. In terms of the deposits, excessive deposits on the HP evaporator and boiler water wall surfaces, and most often no samples taken for analysis. I'll show you this in detail in a few minutes. Delayed chemical cleaning, and these are all addressed in detail in the IAPS internal deposit technical guidance document. In terms of contamination, repetitive contamination above action levels, sometimes even above shutdown limits, no operational management support for unit shutdown. So these are some of the contaminant ones that we have, and these are all addressed in the 2 treatment documents for volatile, as I showed you, and the PT and the CT technical guidance document. These are in the contaminant section of those documents. And the one on instrumentation, lack or reduced or out of service online instrumentation, and very common use of only grab samples to control the chemistry. And these are, again, included in detail in the instrumentation guidance document. So you have IAPS guidance documents here for basically all the RCCS that we've come across. Maybe you have a few different ones, but the guidance documents address all of these. So let's have a look in just quickly at some of the details of the corrosion product ones, because they're the important ones. So here we have technically we have something old and something new. The old is the original IAPS document on corrosion products that's given down here, and this includes all the information you need to know on sampling and locations of where to take those corrosion product samples, how to do the analysis, and most importantly, that you need full digestion to make sure that all the particles are solubilized so we can do the analysis properly. And the next slide shows the famous achievable levels. This is the achievable iron and copper levels for different types of plants. And this, I emphasize, is for steady state base loaded plants. So for instance, if you have a fossil or a combined cycle plant operating on AVT, you would like the total iron levels to be less than 2 ppb. If you operated on an oxidizing treatment such as OT, then you would want the iron levels to be a little lower than that. Here's the same value for drums on HRSGs. Here's the values for units with air-cooled condenser at the air-cooled condenser outlet in the condensate system, less than 10. And if you use a post-condensate filter, we like 5 micron filter, then you would be hoping to achieve less than 5 micrograms, 5 ppbs. So this gives you an indication here that if you have higher values than these, then when we go to plants, we would rate that as an RCCS. You can rate it yourself as an RCCS and address it. So welcome to everybody, according to Scott, thank you. So now what I wanted to go is almost a brand new IAPS white paper, which we just published. And this is for fast start or frequently started plants in comparison to the steady plants that we've just talked about. Here, the important corrosion product indicator is how quickly the iron decay takes place from the high shutdown level during startup. And this can be monitored using proxy techniques such as turbidity. And you can see here's an example of it from some of the work we did in developing this. You can see that here's the decay profile, as we call it, and these vertical lines here indicate what's happening on the unit. So gas turbine fires, makeup additions, synchronization, and this is the calibration. This is the calibration curve. So once we had this, we then needed to have a tool to be able to make an assessment of whether this profile is good or bad. And this is one of the most exciting things that I've been involved in for many years. This is a really excellent tool, I think. Is that here is what we call the IAPS corrosion decay map, and you can see that it has basically 3 colors. If that decay profile is in the green, it essentially translates to that a particular unit has the optimum operational chemistry and shutdown chemistry. If it's in the red, completely opposite, poor operational and poor shutdown chemistry. At the bottom here, we've just put the levels from that achievable table that I just showed you. And so here's the first example. So this is that profile that I just showed you that we developed, and it's been superimposed on the decay map. You can see that it's basically in the green area, suggesting that it's optimum operational and shutdown chemistry. It comes almost down to the achievable level in a couple of hours, which is good. This is for a well-operated combined cycle plant operating on AVTO, but using dry air preservation of the boiler. So good shutdown protection as well. So contrast that with these two examples. These are examples from plants that need to improve the operation and or the shutdown chemistry. So in this case, this is again an all-ferrous unit operating on AVTO, daily load cycling, and start up in 60 megawatt increments. And now you can see that this decay profile is into the red with very high levels. So the total amount of corrosion products, iron, that's transported will be very high. And you can see that those high levels essentially last for 4 or 5 hours. In this case here, this is another example, another all-ferrous system operating on AVTO. As it has some shutdown, some shutdowns with no protection. And in this case, the profile doesn't actually go into the red, but you can see it remains high for quite a long period of time and does not come back down to the achievable levels until 6 or 7 hours. So a large amount of iron being transported into the unit. So from the point of view of RCCS, if the decay profile is in the red or the yellow, then we indicate that that's an RCCS, and you can do the same. You can do these proxy tests very easily and superimpose them on the IAPWS map and see if you have RCCS. So the new white paper also includes something I think that's very useful, possible uses for the decay map. So the first one, obviously, I think should be obvious. It provides some fine tuning of the cycle chemistry and shutdown procedures of a unit. So this minimize the iron with the decay profile moving to the green. The way that I look at these is not the absolute values of the iron levels, but how quickly you can move that decay profile into the green area in the lower left part of the diagram. The white paper in section 10 provides you an indication of what optimum chemistries are, and of course non-optimum chemistries, and it includes that for all the different types of units: supercritical, drum units, combined cycle. This is very, very powerful. This is for all the units that exist in the world. You can go to this section 10 and see what's good and bad. You can also use it for units with an ACC. If you've been operating with a low pH and you've got very high levels of iron, then you could increase the level of pH and watch the iron level come down. Again, you want it to move towards the green, towards the lower left. And of course, we're also starting to use this now in the application of film forming substances, which hasn't been done before in detail. This is also very powerful in the work that we're doing in film forming substances. So hold on, just have to get to the next slide. So now I want to move on to the second area that we selected, and this is for deposits on boiler water walls and HRSG HP evaporators. And these are important because these are precursors to under deposit corrosion mechanisms. And up to about 15 years ago, there was very little that was known about HRSG HP evaporator deposition, as very few tubes have been removed. We published the first story. My colleague and I at Structural looked at 45 samples, and we developed what I'll show you in a minute is the deposit map. Now we've continued, and others are doing the same, and we have more than 150 plants now in the database. And the actual format of it has not changed at all. So let's have a look at some examples of what an optimum chemistry, optimum HRSG chemistry. You take a tube out, it would look nice and red and smooth like this. And when we take a cross section, the white area is the tube, and these are the deposits. You can see pretty low level here, and you can notice that the deposits themselves are particulate, and the most important thing is that there's no concentration at the base of the deposit. So this is a very good. Contrast this with an HP evaporator, a non-optimum chemistry using AVTR. When we take the sample out, they're usually black on the inside, and the deposits are very thick. You can see here much thicker than what we've just seen, and then if we do a little bit more analysis, we can see that in these heavily deposited areas, this is the deposit right here, this is the tube. You can see these dark areas along the base of the deposit right here. We call these reaction products. You can see them highlighted with sodium phosphate right here. We don't want to see these because this means that you can have concentration of chloride as well and end up with under deposit corrosion. So this is an important aspect of preventing under deposit corrosion, is to identify not only the deposits and what the levels are, which a lot of organizations do, but also identify these corrosion reaction products, which are these dark areas right here. So this is in an HRSG. We see the same thing in fossil boilers. Fossil boilers, this is just an example with rifle tubing. Here you can see the reaction products right here and right here. And then this is the important item here, that these reaction products indicate the deposits are heavy enough to allow concentration of contaminants, that's mainly chloride, and can lead to under deposit corrosion. Hence, when you see these, then this would indicate an RCCS. So let's have a look at the map. So this is the IAPWS deposit map, which we developed a few years ago. You can see here's the deposit loading right here. If we take a tube out and it's in the green area, then we expect it to only show particulate magnetite in the deposit with no concentration. But once we get to the top of the yellow band or into the red area, then we would start to see that concentration. And this means that that these should be cleaned, because if any contaminant gets in, it can concentrate in the same way. And so these are a couple of examples. We use it for other things now. As I mentioned, we use it in our film forming substance work that we do. And so what we try to indicate in section 8 of the guidance document is please don't add a film forming substance if your HP evaporator looks like this. So you can see here's the deposit level up to 65, and you see this concentration along here, and 65 is right up here on the map, almost right off the map, and therefore gives the possibility that you could increase those deposits and get a level of under deposit corrosion. And this was just an example to show you that this is one that we looked at. So this shows after some time, after more than 10 years, we had a total loading up to about 25 milligrams. This plant then decided to use a film forming product. That's the non-amine version of the film forming substance, and tripled the amount of deposit very quickly. So please be very careful if you're adding film forming substance that you've looked at your HP evaporators. Go. So this is the second one of these little tables that I developed to show which of the RCCS which lead to HP evaporators, and indicate that all of these here have an IAPWS technical guidance document to address them. So again, this is just repeating really, if you have a situation with corrosion products, with the levels exceeding the guidance, or having the decay profile outside of the green area, then you would want to review these documents and operate to these guidance documents. There's, as I already indicated, there's a technical guidance document for film-forming substances. Not challenging the status quo, which is very, very common in this area. Not using the correct feed water chemistry. So I outlined these previously for you, and using a reducing agent. That would be in the two main treatment documents for all volatile treatment and for PT and CT. And then, as I just indicated, not removing tubes for analysis and not using the IAPWS deposit map to see where you are, then this would be covered by the internal deposits technical guidance documents. And anything to do with instrumentation to see whether the chemistry is okay or not, then this would be in the instrumentation. So again, you see for this very important mechanism, that all the RCCS which actually lead to HP evaporated deposits have a counter in terms of the IAPWS technical guidance documents to address them and to prevent them. So let me just move on here. I'm going to now talk about flow accelerated corrosion. We don't, of course, have sufficient time in this 45 minutes to talk about this in detail. Sometimes I give workshops for a whole day on flow accelerated corrosion. So I'm just going to try and highlight the key parts, which in the terms of today are the RCCS, because FAC is influenced by multiple RCCS and controlled with IAPWS technical guidance documents. So let's just have a look here. We have very extensive records in terms of where FAC exists. And if any of you want to go any further, at the bottom of all these slides, there's references here. Scott has a special page where he can reference these. These are available freely to you on a website somewhere, and he'll provide that to you. But we have this very excellent understanding of where FAC takes place in a single-phase version and a two-phase version for HRSGs, and similarly for fossil plants. So again, the single-phase FAC items are right here, and the two-phase ones are generally in the drain lines and the cascading drain lines right here. And if you want to know any details about it, please go to this reference where it's very extensively covered. So I wanted to indicate that the situation with FAC is still occurring, and still occurring in not a very good situation, possibly at the same rate as it has for the last 10 or 15 years. All the examples of FAC are numerous and published. There are basically no new locations or situations over the last 15 years. But the real item from a chemistry point of view is this at the bottom, where single and two-phase FAC are still occurring and not being identified uniquely. This is one of the most important things in the FAC control, because these two types of FAC are controlled differently from a chemistry point of view. And again, the published documents indicate this in great detail. So let me just show you a couple of examples here of what to look for. So this is an example of single-phase FAC, and many of you will have heard of the orange peel appearance, which is like this or like this. But the real thing that indicates whether it's single-phase FAC is where the FAC is quite as severe. And you see this line here of chevrons or horseshoes. What we say is the horse is walking in the direction of flow. And this is the key indicator for single-phase FAC. Whereas if we have two-phase FAC, the surface appearance is very different. It's usually black and shiny, just like you see here. And when we look at the area where it's not quite as severe, you will see this sort of appearance. We call these FAC dimples. And these are the dimples that you see. They generally don't have any directionality. And so they should be very easy to identify. But this is very often misidentified as single phase FAC, and the plant is trying to solve the problem by adding oxygen. And I have to tell them that they can add as much oxygen as they want. They will not turn off this FAC. So it's very important that you identify whether it's single phase or two phase FAC. And then if you take the metallography a little bit further and look at it in a scanning mic, we generally see this sort of appearance. These are called the scallops of FAC at a microscopic level. And so it's most important to identify that the failure mechanism that you're dealing with is FAC, and the type is either single phase or two phase. And you see this appearance in both single and two phase FAC. But you use the morphology that I've just shown you to identify which one. So here's the third RCCS table, which leads to FAC. And of course, here we're not only dealing with fossil and HRSG plants, we're dealing with air-cooled condensers as well. And again, in this exactly the same way as for the others, there are IAPS technical guidance documents to avoid these failure mechanisms. So let's just have a quick look. Some of them are basically the same. So the main one is incorrect feed water, condensate, and LP chemistry. This is the one that I just told you about, thinking that an oxidizing treatment such as AVTO or increased levels of oxygen will address FAC. But it won't, as I indicated, it won't have any effect on two-phase FAC at all. The other item is continued use of reducing treatments. This is a no-no in combined cycle plants and even for fossil plants that have all ferrous systems. We do not want to use AVTR. And of course, the chemistries are included in the treatment guidance documents in the volatile one and the PT and CT documents. You'll see all the information you need in there. Not monitoring the feed water corrosion products to see if you have FAC. I've already covered that. That's covered by the corrosion product TGD and the new white paper that you can do that. And instrumentation, whether you have the right instrumentation, status quo, using the same chemistry since commissioning this, basically the same things as I mentioned already. And you will notice that for each one of these RCCS, which are the things that lead to FAC, then there's a IAPS technical guidance document to address it. So that's so let me move on here. The final one that I want to just cover in the final 5 minutes is avoiding phase transition zone failures and damage. That's in the phase transition zone of the steam turbine. Here's a couple of examples. And just so you know where the phase transition zone is, this is what we call the Mollier diagram. And this is the steam expansion through the turbine. This last part is through the LP. And this is the red is the saturation line. And this is the phase transition zone here, where obviously the phase transition takes place. And so this is the important area in the low pressure turbine. These are just some examples. And the important thing to note is that the chemistry activity in a steam turbine, that all phase transition zone failures initiate at pits. You can see many examples here. This is a pit, initiating at a pit. And the next slide just shows the same, a little bit more detail, but at the metallographic level, you can see right here, the pit, stress corrosion cracking, initiating at a pit, at a pit, at a pit, at a pit, and at a pit here. So this is one of the common features that we see. So to understand this, you have this number of things very complicated mechanism, but we've identified it with some with IAP's help and some with other work that was done. Some of it supported by EPRI when I was at EPRI, by Palmer and Simonson. And for the mechanical carryover, this is the carryover document. You can see that when you measure the carryover at any of the pressures, you want the mechanical carryover percent to be less than this solid line here. And so this is for mechanical carryover. If you operate with a high pressure unit above 2300 psi or 16 megapascals, there is a very small effect of the volatile carryover. But at 2800 psi, the volatile only represents a very small amount, much less than 0.1%. So, but we find many plants do not measure carryover, and that's a really important item. There's also some items that you need to think about in terms of these mechanisms won't take place unless there's any moisture. So we spent a lot of time identifying many years ago what the moisture and early condensate and the liquid films on the blade surfaces look like. And so when you look at the moisture formation, that's the condensate that forms. We have concentration ratios up to about 100 times. Concentration increases with decreasing moisture. The closer that you get to the actual saturation line, the concentration will be higher. The droplets are typically 0.1 microns in size. Their formation is influenced by surface tension. There's essentially no oxygen in that liquid, even though you might be operating a unit on oxygenated treatment. And for the liquid films that grow on the surfaces, they range up to this sort of level. They're very variable. Concentration factors can be another 10 times, and again, there's no oxygen associated with those liquids. And I produced this little diagram many years ago just to illustrate this. You can see that this is the phase transition zone. So these are the L-0 or L-1 blades. This is the droplet formation here and the film formation on the blade surfaces. And then this environment here goes to the condenser or acts as the air-cooled condenser initiating environment. And so it also is recognized that salt crystals deposit onto the blade surfaces on units even with the best steam purity. And this is the reason that we have to provide protection, if possible, with dehumidified air to stop these crystals changing into or transforming into a pit. And so this is just an example. So this is the internal surface of a pit here that's already formed. And when the liquid film forms and the stress involved, you can get a microcrack forming like this. And this is the actual failure of the blade, right here. So again, this is the same slide that I've shown you a couple of times now. This one is for the phase transition zone. And so some of these are slightly different than the other ones, but so what we find is RCCS might be repetitive contamination above action level and no action, contaminant ingress above a shutdown limit, and continued detemperation during contamination. And these are all addressed in the steam purity document, which has a very nice description of the process. And the contaminants, of course, are controlled by the treatment documents. So in terms of instrumentation, lack or reduced instrumentation, the most common one in this area is no steam monitoring, which is kind of quite amazing, but that's included in the instrumentation guidance document. No knowledge of carryover, as I've indicated. This is how the impurities get into the steam. There's a carryover IAPWS document. and the other one's the same. So again, as with the other ones, all the RCCS, which are important and control these mechanisms, have all been addressed by IAP's technical guidance documents. So you can go to any of these for any of the mechanisms that we've talked about and find the correct way of overcoming them. So this is nearly at the end here, just a couple of slides. So this is an example of a dehumidification system. This is on a mobile skid. This is actually on supercritical units, and they move this skid to the different units and provide the dehumidified air through the extraction lines. And this is a very nice system. This actually followed a failure, and so wherever the dehumidified air has been used, we haven't had any subsequent or initial failures. So the last slide, I think, is right here. So this is a few closing remarks that I have. So I think I've indicated that RCCS relate to the very basics of power plant chemistry and thus to plant reliability and performance. We find that individual RCCS are generally not a problem. If you only have one of them, it should be addressed, but it doesn't link synergistically with the other RCCS, which result in the damage. But more than 2 or 3 means that the plant has or will have a problem in the near future. We have a large database that indicates this. Each repeat situation for each of the damage failure mechanisms can be addressed by application IAPS TGD and now the white paper. And as I showed you on that table, the most important RCCS are corrosion products. These represent 85 to 90% of organizations out there that have this RCCS. Deposits, instrumentation, and the status quo. And film forming substances, we haven't had time to cover those. I couldn't cover everything in the short time period, are covered by 2 IAPS technical guidance documents. Recent analysis confirms that Section 8, which is the main section in the film forming substance guidance document, should be reviewed with particular emphasis on those internal deposits. And steam turbine protection, which we just covered, which represents for the dehumidified air part more than 90%, be careful with the change of operation, and particularly as we now find more units operating flexibly and a number of them changing from 2x1 to 1x1, this changes that expansion and changes the phase transition zone. So these are this is where I'm supposed to finish, and there's one more slide here, which I think Scott has already covered. I hope that you've gained something out of this. Thanks for your attention, and I hope you have some questions and or comments. And Scott is supposed to have been collecting them in the chat for us to deal with. So that's all I have to say. Thank you very much for listening.
All right. Thank you very much, Barry. Can you see the chat? Because there's a few good questions in there, or do you want me to translate them out to you?
Just hold on, because I can't see them at the same time. I have to just get rid of this and then expand this one. You can read them while I'm trying to find them.
Yeah. So the first question is from Kyle, who's just asking about when should the first HP evaporator tube sample be taken from HRSG, and how often afterwards? Should the sample be taken from the front row or back row of evap tubes? How far up the wall should the sample be taken?
Yes, the database that we've developed is essentially for the lead tube, and within a couple of feet of the outlet on our horizontal gas path unit, and we look at the lead tube, and in the guidance document there is a suggestion that if you haven't taken a sample within the first 20,000 hours of operation, you should do that. And then depending upon that analysis, that'll tell you whether whether the deposits are in the good area or not so good area, and that will indicate to you the time that you should choose to take the next sample. So I think that covers all of them, David.
Yeah.
And I'm just still trying to find the chat. So
That's okay. Okay. The next question was someone, Kyle again, wanted you to elaborate on the iron measurement method used to plot points on the iron corrosion product decay map, and where the sample locations for those samples. And I think I can probably predict you're going to suggest here's a look at the TGD.
Yeah, so you can, yeah, I mean, I anticipated that most of the questions are already covered in the TGDs. That's what I mentioned at the beginning, is that there are many parts of those TGDs that are not followed exactly, and we get questions like this. So the general suggestion is that there's a uniformity, and that's what the database sort of requires. And we look at economizer inlet generally. So economizer inlet in a fossil plant is the economizer inlet, but the economizer inlet in a combined cycle plant is usually at the boiler feed pump. And so we usually use that. And then if you use those points, you can directly compare with the table that I showed you. And Scott has put up here the references, and you covered at the beginning the technical guidance documents where you can get those. You can get those as a PDF. The white paper is a little bit more difficult to find right now, but as you know, it once you know where it is on the PCC page, it's quite simple. So I think that covers those, David.
Yeah. I'm just going through the ones. Some of these questions, unfortunately, for the attendees, they're quite difficult without knowing a lot of detail of the plant. They're very plant specific ones, so we might have to park those ones. There's a easy question here. Iron analysis, should that be performed with or without sample digestion, Barry?
Yeah, well, I included that on the slide, David. I mean, that's one of the main activities that's missing. It's when we initiated that guidance document in 2014. That was one of the reasons that we did it, because so many organizations were just using the spectrophotometer in the laboratory and not digesting. And so we're gradually getting that message out. I think there's less of those situations right now, but otherwise, if you do not do that digestion, you're only talking about roughly 5% of the total amount of iron that's being transported.
All right. There's probably an interesting question here from someone about how long does it take to achieve stabilization of cycle chemistry parameters after starting the HRSG on a combined cycle unit. So I'm assuming they're asking in terms of a cold start. I know what my experience is, Barry. What would you say in terms of stabilization to get into steady operation?
Just go ahead and give your answer, David, because there's no uniform answer to it, right?
So well, the answer is if you are an IAPS optimized plant and you've applied good layup and storage during that shutdown period, you should be pretty close to stable kind of baseline values after somewhere between 6 to 12 hours. The longer time will be for a cold start, and for a hot start, you can be a bit shorter. But it depends on lots of things. It depends on the ramp rate and how stable you are in load. But the big thing is it depends on how well you are managing your chemistry and your makeup water purity and condenser tube leaks and dosing control. So it does vary.
And I just want to emphasize again, because I'm so enthused by this new decay process, that we have for the first time an ability to be able to indicate whether the normal chemistry and the shutdown chemistry are optimum or not. And that's really powerful. That's a really powerful tool, I think. Once a lot of organizations start to use it, they can then provide that answer themselves.
Okay. This is quite an interesting question here. It's probably worth having a little chat about. Someone's asked, they've said, any special treatments recommended for steam turbines and steam generators required for a unit, which is a coal-fired supercritical that operates in base load for 3 to 4 hours, and then the rest of the time at 30 to 40% load, and 2 shifting during the weekends?
Yes. I'm not quite following the question. There's no concern in that operation for having the initiation of pits. We generally would say that has to take 2 or 3 days, depending upon what the machine is. And so, you know, the chemistry that you use then would be exactly as described in the treatment documents. And the key situation is if that shutdown period goes longer than that 2 or 3 days, that's when you have to start worrying about whether you're likely to have any condensation during that time, which could initiate pits on the surface, which are the start of all these failure mechanisms.
Yeah. Now we're probably pretty much out of time now. Did you want to do any more questions, Barry, or do you want to leave it there?
I thrive on questions and criticism and comment. You know that.
Yeah.
And my suggestion would be, like, whenever we do these things, there's always a lot of questions. I gave the people here my email. It was on the last slide. But Scott can easily put it up on the screen. I have one at my work address at Structint, or one at IAPWS, and any people who are on the line here can contact me, and I will, as you know very well, respond within a day back to them.
Yeah. Okay. Well, here's an interesting one. So someone called Jorbit. Have you encountered a low pH in the IP drum? So we're assuming this is a combined cycle unit, where they're getting a pH of 8.8, even though their economizer pH, their feed water pH, is 9.6 to 9.8. There is no change in pH even when we inject phosphate in the IP drum.
Yes. I thought you were saying there was a low pH.
They're seeing a lot. They're seeing a low pH, and then they're saying that they're injecting phosphate but not seeing a change in pH. My suggestion would be check the calibration on that pH meter first and foremost.
I see. He's saying that you don't have a change in pH when they add the phosphate. That's what he's saying, I think, right?
Yeah.
So I would just say that it's probably the most common situation for a triple pressure HRSG, and there's always a lot of concern about that pH and how that changes in the IP drum. I'm not too sure about the addition of the phosphate, or even know what it is. Hopefully it's TSP at 4 or 5 ppm, and it should have an effect. But losing the pH in the IP drum is always a situation.
Yeah, I mean, if you're dosing something that's meant to raise the pH and you're not seeing that effect and you're confident in your instruments, it's normally check that you are dosing what you think you're dosing.
Yes.
and check that it's dosing where it's meant to go. And sometimes you do find that valve lineups and dosing connections sometimes on new units aren't what the drawings say they are. They've not been constructed properly, and you have to have an outage and confirm that you've got flow through the pumps
Yeah.
and things like that, and make sure that you've got mixing and distribution. So you just have to systematically go through normally and identify, have you got a mechanical issue, have you got a chemical issue, and then have you got some kind of flow circulation issue going on.
Yeah. Yes. And yeah, I would say that many plants in this situation don't monitor the phosphate properly. You know, they do it once a shift or twice a day or whatever. And we would suggest that they monitor the phosphate continuously in that situation.
Yeah. So
Yeah.
sorry, Joel, but we haven't got the answer for you because we just don't have enough information to be able to diagnose what might be going on there. But
it's a common problem.
yeah, someone's just asked, what is the meaning of RCCS? And it's a repeat cycle chemistry situation.
Correct. There was one here on my screen. High level of oxygen more than 100 ppb is risky if we have oxygenated treatment, and the target is 90 ppb. From somebody, Same Tadros.
Yeah.
It's not actually true. It would depend upon what unit it is. We would want to know what type of unit was it. If it was a once through unit, a conventional fossil plant, there would be no concern whatsoever.
Yep.
If it's a drum unit, there would be a concern if that oxygen level at the economizer exceeds the recirculation ratio, and same for a combined cycle. The same for a combined cycle plant. So that has to be defined by an actual unit. If Mr. Same contacts me, I can reference it for him.
Yeah, it's wanting to stay below that 10 ppb in the downcomer on a drum unit, isn't it, Barry?
Well, that's the recirculation ratio. So you know, you're talking about for a normal drum unit, you know, operating at say up to 2500 psi or 16 or 17 megapascals, you'd be talking about recirculation ratio of 3 or 4 probably.
Yeah.
And so
they've just confirmed in the chat it's a once through unit, so 90 ppb, 100 ppb.
So we have, it's probably the most common question I get about units on oxygenated treatment. You know, there's really no control for oxygen. When I developed the initial guidelines, we set a limit just because plants like to have a limit, but technically there's really no reason to do that unless there's an increase in case in cation conductivity. If there's increase in case, then you would have a requirement where you would have to control it. You don't want the case to go above 0.3 microsiemens, but otherwise, I'm not concerned about oxygen at all.
No.
In the case that he mentioned.
Yeah, I mean, probably the most important thing is what is the total ion levels in the economizer inlet in a once through unit, and you have to make sure that that chemistry, that oxygen and that pH is optimized to give you the lowest possible total ion at the economizer inlet. And in a once through unit on oxygenated treatment, you should be able to get that well down below half a ppb or even less in an optimized system. And that's really the goal.
Yeah. Okay, so Scott, I just want to make sure that you know, at the bottom of all my slides there's references. I think most of them, maybe with the exception of the steam turbine ones, are on that site that we use. Can you confirm that?
Yes, Barry, and then I sent that link out, and we'll get it updated as well if anything's missing.
Okay. Mr. Rizwan Ali here is asking about the presentation. As I understand, I may be talking out of turn here, but we usually, when we run these things, we would have in a week's time or something like that, whatever time Scott decides on, he would put them at a central location and let everybody know. Is that the correct way, Scott?
Yeah, we'll be posting it on the IAPS website, and we'll send out a notification as soon as it's available.
Yeah. Remember
Okay.
that we're running a second session of the same presentation in a day or two's time, just to cover other parts of the world, and then once that's done, they'll be all made available.
Okay.
Yeah.
So
Right.
yeah, he says kindly share the presentation, no problem. And he says it's one through unit, so that's okay.
Yeah.
What is the meaning of RCCS? Mr. Seshu can come on Thursday again if he wants to.
Yeah.
We inject, also check phosphate levels. Yeah, okay. I'm just scrolling down them now.
Yeah.
Yeah, okay. It's okay. Are you recommend the injection of ammonia in AVTO treatment in LP drum? There's a Mr. Ali here asked about the injection of ammonia, David.
Yeah.
And whether we would suggest to put it into the LP drum. It's not my preference to do that. Preference is to put it into the condensate, but some organizations can put it into the LP drum if you want to. It's not a big deal, I don't think.
It would depend on that particular HRSG design, what you can do, whether it's supplying the LP drum is supplying a temperation water as well. So it would depend a little bit on the design.
Yeah, okay. So have any of you got any other questions? I've already given you a route out. Just contact me. There's no problem. We will get you answer. I'd like to see everybody reading the IAPS guidance documents and the new white paper. And David, we should just mention that one of the reasons that we issued that corrosion product with the decay map as is because we are hoping that people will take it and use it. It's very easy. Many plants already have the proxy equipment to do it, and then send us their data superimposed on the decay map. And that's how IAPS moves forward. We can then improve the relationships then by doing that. So hopefully many people on the call will use the guidance document and the white paper, and please feel free to send me the information, or else if you're in an IAPS country, then you can provide it to the IAPS representative in your country. No problem. So
and for everybody listening in, these types of discussions are part of IAPS and our annual meetings. There's lots of conversations like this and lots of good discussions that go on both officially in the meeting and on the edges of the meeting as well. And it's all about sharing information and experience and knowledge to help people prevent them from having repeat failures and having common problems over and over again. That's part of the goal of IAPS.